Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today we are discussing a very important application of vacuum technology leading to several other technologies, that is vacuum based coating units for thin film deposition. In this lecture the concepts covered are: we will introduce the coating technology and need for vacuum, etc. We will also try to talk about vacuum based coating methods and their applications in general, so that you can get a idea of the technical aspects of coating systems. Then we will go to physical vapor deposition using thermal evaporation and laser beam evaporation, etc. They are all physical vapor deposition systems. We will also see electron beam and sputter deposition methods. They are in a way vapors, but methods are slightly different. So, sometimes electron beam can be called as a physical vapor deposition, and sputter deposition is a separate technology, but we normally club it with these things. But there is another route altogether, that is called chemical vapor deposition. That is somewhat different in its aspect in various technicalities. So, what we thought is the PVD methods are having applications in metallurgy, coatings and optical and various other engineering applications. But CVD along with PVD will find huge applications in semiconductor industry, which is a very big industry. Modern day world depends heavily on electronics. So, what we finally decided is to separate the CVD and semiconductor as a separate lecture, where we will be covering CVD technology. But that is also basically a thin film technology. Sometimes people call it as thick film technology. In fact, in literature you will get lots of jargon, coatings. Somebody will say thin film, somebody says thick film, somebody says film, somebody says layer. Okay. And there are associated terms called interfaces, surfaces, etc. But basically everything is nothing but a two-dimensional structure. You can call it a film, but it is a two-dimensional structure. That means, the third dimension, the so called thickness, is much less compared to breadth and width. So, a layman can understand these coatings are solid state materials in the form of thin films. If it is very thick, millions of layers, then it becomes sheet, and if it is very thick, then it becomes a bulk. So, the phenomena associated with thin film is slightly different compared to sheet metal, compared to a bulk metal. So, what we are going to discuss here in these two lectures, PVD and CVD and semiconductor, we will not go into the details of semiconductor manufacturing or metallurgy or anything. We will tell the applications, but we will concentrate more on the role of vacuum in PVD and CVD etc., how the equipment look like, what is the physics behind it, because that is important. Once you enter into a semiconductor industry, they may not be able to explain the physics behind it or anything, because there are standard routes you will be employed to do a particular thing and keep on producing. But a time is required for you to understand what is it, what is the science behind it. That is why we are keeping 2 lectures on thin film technology or coating technology. It can be industrial coatings, it can be very important high tech thin film coating units under a broad category of physical vapor deposition and chemical vapor deposition. Within that, electron beam deposition will come, sputtering methods will come. We will try to conclude, depending on the applications and depending on methods, what is the present status and why is it important and what we should do about it. So, a little bit of economics and technology based on these coatings we will be covering. Separately, we will cover some other technologies based on these things in an indirect way in solar, semiconductor and metallurgy, nuclear or even space or even cryogenic technologies, where they are basically films, but there the concentration is more on the applications. But here the concentration is more on the deposition technology and associated vacuum aspects of it. Why I am giving this much introduction here is, if you do not understand these thin film deposition methods, just if you enter into semiconductor industry or any optical industry or solar industry or any other industry, even capacitor industry etc., you will not be able to appreciate the physics behind it. That is why we are keeping a separate lecture on thin film deposition methods. So, I told you already the thin film technology can be also called coating technology. So, vacuum based coating is nothing but a 2-dimensional film on a surface deposited under vacuum conditions. It is called deposition. For our students, they know very well. I am talking in the form of layman's language, because some school children also are going to take up this course and they need to get a feel of it. It is basically a 2-dimensional film. Just I will an extension of this, we will come back to the lecture little bit. A 2-dimensional means what? Third dimension is much less compared to these 2 dimensions. And after creating these 2 dimensions, when you try to scratch and make 1-dimensional long thin films, but in a long rod type of thing, but it is not a real rod, thickness is very small. Then further when you try to cut it in horizontal direction, then you will get a small aspect of that thin film. What I am talking in a layman's language is exactly VLSI technology. That means, you make a film, you try to deposit a film first and do some operations which I do not think you can understand very fast. There are oxidations and dielectric coatings, metallizations and varieties of processes, but all of them are coatings. Then try to cut them using lithographic technology and masking technology, and try to do some ion beam into that, so that you will get p type, n type etc., and again put some oxidation and try to put some dielectric layers. So, variety of these things will create the most important devices known as semiconducting devices. So, that is what I want you to understand. This knowledge will be useful there, but the knowledge of thin film coating is also useful in optical coatings. For example, a thin coating, anti-reflection coatings, they are also applications of thin film. Methods will be similar, whether it is a physical vapor deposition or chemical, depending on the cost economics. That is a different thing, but they are all used in public life, whether it is a film deposited using a plasma technology or a thermal evaporation or an electron beam or sputtering or molecular beam epitaxy. Depending on the quality of the film, chemistry of the film or the application of the film, methods will change, but every technology heavily requires vacuum technology. Otherwise, what will happen? Metal becomes metal oxide, because if you want to deposit from a bulk, you have to physically evaporate, melt and evaporate and coat it as a film. It is like if you try to heat some carbon dust or something, vapor will come out and gets deposited like various small powder, etc. It is a film, basically thin film technology which you apply on the surface. Same thing here also. So, I want you to appreciate the modern world is basically going smaller and smaller, faster and faster in time. Smaller and smaller is possible if you try to reduce 3 dimensions of a bulk into 2 dimensions of a film and later into 1 dimensional like quantum dots, etc. So, thin film is going to play very, very important role. What are the applications? As I already hinted to you, laptops, mobile phones, LED TVs, coated spectacles, solar PV coatings, solar thermal coatings with high emissivity, low emissivity, etc., diamond coated machine tools with huge strength in a thin structure, as a surface engineering on metallic substrates, and decorative coatings and day to day life. Even the package material that you are using, it is nothing but a plastic paper on which there is a coating, shiny things, and even this watch, gold looking, it is not gold plating. I cannot leave it like that if it is a gold plating. It is basically titanium nitrides, these are all coatings, very hard coatings, but thin coatings. So, multiple applications are there on even household utensils, packaging materials, everywhere you use these coatings, they are called engineering coatings. Microscopically, they are called thin films. And several industrial processes use these metallic coatings for wear resistance, corrosion resistance, thermal resistance, and sometimes they use metallization for electrical transport in micro electronic circuits, whether it is a microwave circuits or internally interconnects in a IC chip manufacturing, etc. Depending on the level of microscopic nature and the application, you will have to devise how you are going to make this first piece, that is called thin film. Then use other technologies to do some other applications like VLSI for electronic device manufacturing. Okay. And if it is only reflecting coatings in a mirrors, then it is optical efficiency that is more important. Okay. So, this is overall application potential of thin films, but other aspect from energy point of view, under vacuum, when you are melting and evaporating from solid state to liquid state to vapor state, and sufficiently high temperature, that becomes almost like gas, and then you try to deposit on a substrate which is kept in a particular distance. The distance between the source of the material, which is a bulk, and the substrate on which you get finally this thin film, that distance should be smaller compared to the mean free path. Then you will get a controlled film deposition, and in between the molecules are not meeting with other molecules, they will not get oxidized, because mean free path is much longer. Before that, it has reached the substrate which is cold, from hot surface it has come to as a vapor each molecule, and they got deposited. When this will be possible? When the mean free path is longer compared to the dimensions between the source and the substrate. That will happen under vacuum. So, 10 power minus 5 star, minus 6 star, where the mean free path is approaching 20 centimeters, 40 centimeters, 1 meter, whereas the gap between substrate and the source is only 10 centimeters. Then we end up in a situation where we can control better, and we will not have oxidation, and we will be depositing slowly and steadily, or we can deposit very high speed if you want, depending on the application, whether you want an amorphous thin film or a semiconducting thin film or a metallic thin film or a crystalline film, sometimes polycrystalline films. I am giving jargon of these things because you will find in these things in various applications. For lack of time, I am only giving jargon, but I will be explaining methods now. Okay. As I already explained, the vacuum coatings are broadly classified into physical vapor deposition and chemical vapor deposition. In physical vapor deposition, the material to be finally deposited in the film has to be heated from a solid state to liquid state and then vapor state. Using some electrically heated or laser beam heated or electron beam heated, heating method is your lookout, depending on the economics and technology available. In electrical heating, which is the most popular, using some molybdenum or tantalum or tungsten or niobium filaments or boards, you pass a high current with suitable current feed throughs in a vacuum bell jar, which is evacuated by a diffusion pump with a rotary pump in olden days. Nowadays, turbomolecular pump, cryo pump, etc., backed by a rotary pump. If it is a huge quantity or large chambers, roots blower, all these technologies we have discussed earlier, they will be used here to get 10 power minus 6 torr. You can go to 10 power minus 8 torr, minus 10 torr, then quality will be much better. Depending on the requirement of the quality, the vacuum level will be different. But in physical vapor deposition, basically it is physically it is vapor is coming and that vapor is getting deposited using thermal methods or scratching methods, etc. In chemical vapor deposition, the style, the physics and chemistry are slightly different, where the material being deposited comes from a chemical vapor which is produced separately, a so called precursor, that is decomposed by reduction or thermal decomposition. It is a chemical physics. It is not physically a material is getting evaporated, but the chemistry has not changed. For example, if you take a copper, when you make a liquid, it is copper liquid. When you make vapor, it is copper vapor. Phase is same, chemistry is same, then it is PVD. Whereas, in the precursors with some reduction and thermal decomposition, etc., you create an intermediate precursor from various materials, from various chemical vapors, which may be at higher pressures, but pure impurity should not be there again. Then, in contrast to these PVD methods, the substance to be deposited is either solid or liquid. In CVD is already in vapor phase before it is admitted into vacuum system. Finally, when it comes into the vacuum system, your substrate will be there on which you try to create a film. These methods are more useful in semiconducting applications, in large scale production, etc. And the substance must be thermally excited by means of appropriate high temperatures or plasma before you finally bring these vapors to make films onto the substrate, which will be further subjected to diffusion or lithography, VLSI technologies and architecture of various layers and interconnects, metallizations to produce chips, IC chips. It is a very massive technology. It has entered into a mega giga engineering. Now, people who are employed in these industries, they may not be aware of the fact that why semiconductors are used, why, how it is processed, why vacuum technology, they may not be aware, but they are employed. But with this course, you should know why semiconductor, because semiconductor has got non-linear IV characteristic and it has got a band gap. And why vacuum? Because otherwise it silicon will be silicon dioxide, which is a sand, which is an insulator. So, semiconductor physics using CVD methods, we will separately deal with that. So, with this introduction of PVD and CVD, today we will concentrate more on PVD. This PVD already I explained, I am only reading here, you can also go through it. It can be a cathodic sputtering, thermal evaporation. The chemical vapor deposition I added here, but I will not be dealing because it will be dealt separately. And if you try to do the same thermal evaporation using molecular beams from a solid material, that is solid vapor pressure, not the liquid, under ultra high vacuum, that is called molecular beam epitaxy. And if you try to put an electron beam focused on a big material like this, but whole material is not evaporated, a beam is kept, a locally a spot is evaporated, that is called electron beam deposition. And if you put a laser beam onto something and locally evaporate, that is called laser beam evaporation. Because compound materials, without losing the chemical nature of it, as a whole, if the compound molecule has to be removed, such methods they use laser beam deposition, etc. And finally, you have very ultra high vacuum systems where sputterings are also used, but while sputtering you have to increase the pressure, otherwise sputtering action will not be there. These things we will see in detail in the next slide. So, vacuum coating units are very specialized equipments in modern technology with lots of high vacuum pumps like turbomolecular pumps, gauges and variety of interconnecting pipe, mass flow controllers and pressure controllers and various feed throughs and RF controllers. All this together is the central vacuum coating unit. So, it involves several technologies, you must keep track of it. Engineering applications of these coatings I have already told you, semiconducting chip manufacturing, display technologies that we are seeing here in cell phones, etc. These are also basically film technologies. Vacuum coatings for metallization, any decorative coatings, optical coatings and solar cell PV cells, PV as well as solar thermal, you require lot of deposition technologies on coatings, wear and corrosion coatings, superconducting tapes on which you depend on various superconducting layers one by one. That is a massive technology that is going to come up in future, and packaging technologies, everywhere you require these coatings. I am repeating these things because this is such a big process, thin film. It looks very thin, I am giving only one lecture, but we can give, if you are anybody is interested, we can give 30-40 lectures on films, coatings, surfaces, interfaces for various high tech areas. So, you can approach me later if you are interested in a particular area, whether it is semiconductor or solar or anything, because we will try to give lot more clarity on these thin films and how to assess the quality, etc. So, when it comes to physical vapor deposition, as I already told you, in an electrical heated method, that is simple thermal evaporation. In fact, most popularly this is called thermal evaporation, though you can use this thermal evaporation word everywhere, but this method is popularly called thermal evaporation, because you are passing current through two feed throughs and through a filament or a boat made out of tungsten or tantalum, and keep your material to be deposited here and put I square R heating so much, since it is a bell jar is under vacuum conditions using a vacuum pump here, it is called vacuum thermal evaporation, and it will be red hot and material gets melted and vapor molecules are produced. When I say vapor or vapor molecule, they are different. When the mean free path is longer compared to the distance between this and the substrate, which can be cooled or heated depending on the quality of the film, whether you want amorphous or semiconducting or you want a crystalline film. There are other things in film growth, I am not going to discuss that. So, if the distance is small compared to mean free path, which is possible under vacuum conditions, then they are called molecules. And if the distances are still smaller, it is better, but the uniformity of the film may not be good if you put too short distance. So, there is a lot of give and take you have to do, and if you replace this electrical heating by a laser beam and focus it onto the spot here, and suddenly a flume is created and this hot plasma type of thing, and in that is nothing but ions and electrons are coming out of these surface atoms, and they will be deposited on the substrate which is water cooled. This is also basically thermal evaporation in a way, but a focused thermal evaporation at a spot by a laser beam. This is very popular in nowadays in creating compound films for various high tech applications. And if the vacuum level is very high, you need, even if you are heating electrically, you need not have to heat it to a melting point. Even in the solid, if the vacuum level is 10 power minus 10 torr, even solid has got a vapor pressure at 500 degrees, let us say. If you go to very high temperature, copper gets melted, maybe 900 type. But even at 500, 600, if you take it, vapor will start coming as a sublimation type thing from the solid vapor pressure of that copper itself. So, but they are also molecules. Since the background is 10 power minus 9 torr, vapor pressure of it at that temperature is minus 5 torr, it amounts to a positive vapor molecules coming, because background is minus 9 torr. So, it will not be decomposed, it will not be contaminated. These molecules from various sources, gallium, arsenide, things like that, they can come out and get deposited. This type of technology is called molecular beam epitaxy. Why I called molecular beam here? Because vacuum level is 10 power minus 9 torr. So, mean free path is in kilometers, whereas the molecules which are coming very small in number and they are beams, because through suitable collimation on top of this source you can make it in one direction, because it does not know how to go to other direction. Initially it starts from the vapor and it goes in a first direction, as per the Newton's first law it will keep on, because there is nothing, nobody to scatter it. So, it will go like a beam. There will be another torchlight beam of molecules here, it is called molecular beam epitaxy. Here also molecules, but here it is a molecular beam epitaxy. The epitaxy means layer by layer deposition. Substrate holder will be here with x, y, z and manipulation, tilt and rotation. These are required to create different qualities of films with different angles of deposition, etc. It is a big technology. There will be residual gas analyzer continuously monitoring the quality of the vacuum. Gas inlets will be there if it is a reactive thin film deposition, while metals and coming here, some gases will react in the atomic scale and get deposited, and all of it will be transferred through a gate wall to an analysis chamber, where you will be analyzing whether film quality is good or not, both from X-ray physical structure as well as EDAX, XPS for chemical analysis, etc. All that is a part of this unit. Such units with deposition and monitoring and your analysis, this is a big technology using physical vapor depositions, and such cells are called effusion cells. They are not melting like this, but they are effusing vapors. Well, you read out this matter, you will understand later at leisure. And costly materials you cannot evaporate totally, because we need only microgram from these grams of material. So, why should you waste very costly material? So, this material will be in a water cooled hearth which is grounded, okay, this blue colored thing, and a part of it we can evaporate. How? We can take an electron beam, very powerful beam, which is accelerated by electric fields, HV electric field. The electrons are generated from a thermionic emission from a filament. They are accelerated by the high voltage, deflected by the magnetic field B, and finally falling onto a spot of a material which we want to deposit. In thermal evaporation, we have heated the whole material, but here we are not heating the whole material, spot is heated. So, that costly material is saved and background vacuum is created. So, it like a beams, they will go to the substrate and get deposited. This is called e-beam deposition, and you can go to very high temperatures, because local heating here, energy is concentrated here, thermal, that means electron beam is suddenly stopped and thermal energy is so high, it will be immediately deposited, it will be melting locally. You can laser also, we have done the same thing. In fact, lasers in medical applications, they use on our eye, a spot of it is almost melted and removed type thing. So, laser surgery type thing, but remaining eye will not even understand that, because it is a very small tiny dot, its thermal mass is hardly anything, your systems cannot understand that. Similarly, here the entire thing is at room temperature, a tiny dot is evaporated using an electron beam deposition with deflected by the magnetic fields and accelerated by the electric fields, and electron beam is produced from the thermionic emission. You can go through the literature and get lot of information on this. It is a spot melting, and you can deposit, you can remove this and put another substrate, like the series of depositions you can do of a costly material and high temperature materials basically. Then last method, which is very popular nowadays in electronic and other industries, are sputtering. That means, on a target here holder, you try to put a small plate which we want to sputter, okay, and on either side you create a ground electrode here. Now, you apply a negative voltage, that becomes a cathode now, and through a side arm you produce argon gas here, and entire chamber is evacuated by a vacuum pump. Now, this is my substrate on which I want to make the film, but I do not want to melt like electron beam deposition or physical vapor deposition. I only want to scratch and produce film, and the molecule should not be lost, those scratched molecules. That is why I have created a vacuum, and the mean free path is much longer compared to the distance between the source and the substrate. I maintain all that, and while they are in atomic state, I introduce some argon, so that you will get two actions of argon. These argon molecules, when they enter here between cathode and anode, discharge takes place. These will be ions. Ions will go to negative cathode, on which your material to be deposited is sitting there. So, this high energetic argon ion, this is accelerated by this electric field, goes and hits it, and it will scratch like a machine tool the topmost atoms of that material, and they will be slowly coming. This is that material which is deposited like molecules onto the substrate. Substrate is at room temperature, and that is grounded also, electrically speaking. So, high voltage discharge maintains argon discharge, argon ions will go there, electrons will be lost in the circuit and come out of the vacuum. We are not bothered about it. It is not an electron beam heating. We are concentrating on ions. Ions go and scratch it. Ions are called machine tools. If it is an insulating target, then what will happen is this DC voltages, DC discharge will stop after some time, because there is RF voltage we have to apply. Because if you put DC, if there is an insulator on the front surface, these positive ions get accumulated, and discharge, it will no more work like a cathode. So, you need to put an RF, and RF technology, there is a plus cycle and minus cycle, and electrons being lighter and ions being heavier, etc. On an average, even though it is an insulator, there will be a negative bias. These concepts you can go through in the literature. There is an RF sputtering. So, either a DC voltage or RF voltage, you can generate ions. The ions will act like a machine tools. The film will be deposited by a scratching action, not by the melting action. This is sputtering method. So, electron beam, thermal evaporation, laser beam evaporation, and also DC sputtering and RF sputtering. Well, lack of time, I will not go into details. You can go through these things, or in the later, when assessment or examination time, you can ask some questions. Before examination you should ask. Okay? We will see in the discussion mode. So, to conclude, the public life heavily demands a coating technology. These coatings are engineering coatings, not only in semiconductor industry, optical industry, solar industry, and corrosion industry, and varieties of applications are there. CVD is used mostly in semiconductor industries, whereas PVD is heavily used in most of the day to day applications, and the type of heating can be laser beam or electron beam, or a sputtering, which is a scratching basically using DC voltages or RF voltages. And the coatings are basically metallic coatings, or semiconducting coatings, or optical coatings, or polymer coatings, or a diamond like coatings. So, you can see the panorama of applications of this coating technology. From application point of view, several industries have come up in every country in manufacturing titanium coated machine tools, for example, and decorative coatings like gold equivalent plating type, metallic web coatings for thin film power capacitors. There are a lot of companies making semiconductor coatings for electronic devices, optical coatings for lenses, cameras, concentrators, packaging decorative coatings of aluminum on a plastic polymer layers type of thing, but very nice shiny things, etc. That is a technology by itself, and to make it cost effective is the challenge. and then silicon coatings for photovoltaic solar panels. There is no limit actually, there are a lot more applications, I am only giving few. So, all the above industries utilize vacuum technology of different levels and sophistication for realizing these quality products using a very important technology known as vacuum coating technology. So, in the next lecture we will see little bit of chemical vapor deposition in connection with semiconducting device manufacturing. Thank you very much.